So in this experiment, we're dealing with a reaction mechanism that we have not covered yet in the lecture. So I just want to go through this with you real quick. The reaction that happens is bromination of the alkene or the double bond in this cinnamic acid starting material. And what ends up happening is the two bromine atoms end up adding across the two alkene or sp2 carbons, which you can see the structures of the products in your lab manual, page 51. Now, as far as the mechanism goes, there's two potential mechanisms that are proposed in the lab manual. And just to show you what those two pathways are, the first goes through a bromonium cation. The second one goes through just a carbocation instead of the cation being on the bromine. For the bromonium ion pathway, here's how it is postulated that you could end up with a bromonium cation intermediate where the double bond pi electrons capture one of the bromine atoms, and so you end up with a bromine cation, bromonium cation, and then bromide anion. And what happens is between these two carbons, there's a difference in electronegativity, or difference in the amount of partial charge there is between the two carbons. If you imagine the partial positive charge on this carbon, that's greater because this carbon, this partial positive charge here would be more resonance stabilized by the benzene ring more so than the other carbon. And so for that reason, there's more partial positive charge on that carbon there. And not to mention that this three-membered ring triangle suffers from a great amount of angle strain. And so for that reason, the bromide nucleophile attacks at that carbon, and this will lead to the formation of the four possible stereoisomers. Now, I want to tell you that only some of those stereoisomers are formed in the reaction, and that's what you're going to determine through going through this experiment. Okay? But this is the first half of the mechanism, and in your lab notebook, I want you to write the mechanism going from this to the actual product and draw the product structure in the regular zigzag wedge dash format. And I also want you to write the mechanism using the enantiomer of this bromocation. Now in the bottom, we're going to show you the mechanism involving the carbocation rather than bromonium cation. And in this case, what we're showing instead of the bromine or bromonium ion forming that three-membered ring, if the bromine just takes the pi electrons and forms just one bond with one of the carbons, this is the carbocation intermediate that you get, plus the enantiomer of this. I'll let you draw that. So there's really four mechanism pathways you can draw from bromonium ion pathway through this enantiomer and through the other enantiomer, carbocation pathway through this enantiomer and the other enantiomer of that. Okay, and then once you form this carbocation, the bromide ion could come in either from the front or from the back face of this carbocation. And so in this case, you could end up with two different diastereomers as the possible products. Whereas here, earlier in the bromonium cation pathway, this is an SN2 mechanism. So for that reason, you end up with only one particular stereoisomer product for one pathway. But here you could end up with different diastereomers. as the potential products here. And so that is the difference. From the bromonium cation pathway, you only get a specific diastereomer, but from the carbocation pathway, you can get different diastereomer products. And that's something we're going to be able to determine experimentally, because we can't really tell the difference between enantiomers and their physical properties, but we can tell the difference between the physical properties of different diastereomers. And one diastereomer has a particular melting point, whereas the other diastereomer has a different melting point, and that's what we're going for in this experiment. Now, as far as the setup for this experiment, you will want to do your reaction in a 25 milliliter round bottom flask. And what I would recommend is just weigh the weight of this flask, write it down, of course, in your lab notebook, not on a scratch paper, and then add approximately, just eyeball half a gram of cinnamic acid into this. Now, when you do, I don't want you to weigh this over the scale or the balance, and the reason for that is if you spill any solid, that would go onto the scale or the balance, and that would really mess up the operation of the precise analytical instrument that analytical balance is. So weigh out your weight off of the balance, and once you put your solid in there, approximately half a gram, weigh this on the scale again. Now, you might be asking, oh, well, how can I stand this on the scale? There's a number of things you could do. You could use something like this to make it stand on the scale. This is a lid. That may not be the best course of action. Most of you may want to use a beaker like this and tear the beaker, and then put your round bottom flask on top of it. So there's a number of ways to weigh the flask after you put your solid in. And then you don't want to forget to add your magnetic stir bar, and because you're going to use that. And then on top, and then add your dichloromethane, 3 mils, and approximately 1.7 mils of bromine solution. Excuse me, thank you. Assuming you said bless you. And then you want to add 1.7 milliliters of bromine solution into this round bottom flask. Now, after that you want to clamp this onto your monkey bars in your fume hood, and you will want to use one of these clamps, and always clamp at the neck of the glassware, and of course this is attached to the lattice structure in your fume hood, and then you can place your condenser. Now, before actually place the condenser though, you will actually want to take care of the plumbing. In the plumbing, your water inlet should be at the bottom of the condenser. In other words, water comes in from the bottom and fills up and goes out the top, and then the line from the top will then go into the waste or little sink that there is inside the fume hood. Now, if you're sharing the fume hood, this top line should go as the inlet for the second person's condenser. So in other words, this will connect to the bottom of the second person's condenser. Okay, and then likewise the top goes to the waste. And now, once you take care of the plumbing for this, you can place the condenser on top of your flask, and this should be secure enough for the entirety of the reaction. Have to be tall enough to at least about halfway immerse this round bottom flask into that water bath, hot warm water bath, and that's how you set up your reaction. Now, as far as what temperature of hot water bath you should have, I want you to think about that. In thinking about that though, look up the boiling point for dichloromethane, which is the solvent that's in here. There's no reason to go above the boiling point of the solvent for the water bath. or there's no reason to go above it by too much. So let's say the boiling point, which I'll let you look it up, of the dichloromethane solvent is 50 degrees, which it's not, but let's say it is, then maybe your water bath could only be about 60 degrees, and that will actually bring dichloromethane to boil, because the hot water's bath is, its temperature is at least a little bit above the boiling point of the solvent. Now, when the boiling point is reached for the solvent, of course it will evaporate, and what happens with this condenser that's water cooled is when the warm vapor hits the condenser right here, it condenses back to liquid. The gaseous solvent will condense back to liquid, and then it just drains back into the flask, and then it boils again. The warm vapor hits the condenser, condenses back down into the flask, and that back and forth action, that's called reflux in chemistry. Okay.